As we design increasingly deeper networks, it becomes imperative to understand how adding layers can increase the complexity and the expressiveness of a network. Even more important is the ability to design networks where adding layers makes the networks strictly more expressive. And in this lecture, we will learn a brilliant and innovative design of subsequent deep neural networks, which is the ResNet. Let's start with some motivation first. Until now, we have seen the LeNet, the AlexNet, and the VGG. And it seems that these networks are growing deeper and larger by adding more layers. But hold on for a second. Does adding layers truly improve the model performance? Well, theoretically, yes. We wish to have more nested function classes and nested to our final outputs. And ideally, we wish the loss goes lower and lower. However, in practice, this is not the case. If the function class are not trained well, it might diverge and won't be nested anymore. We call it degradation, which means as we're increasing the depth of the neural net, our model loss rebounded if too many layers stacking together. So, how to resolve the degradation problem? Fortunately, researchers from Microsoft Research innovate the idea of ResNet in 2015. It is the most popular convolutional neural networks for image classification, and the full name is Residual Networks. Here, the residual stands for residual connection, skipping layers in the networks. And ResNet is highly structured by stacking building blocks or layers. And let's first take a look at the block. So this is the basic residual block structure. Compare with the regular block on the left. The residual block contains a main step and a skip connection. Let's look at the main step first. The input X coming in goes through a variety of weight layer and activation layers and got the result named Fx. Right before we output the result, we add a shortcut, which is the identified functions of the input of our Fx. And this shortcut also called a skip connection. So it enables us to get the nested function classes. But then why does the skip connection work? Let's take a look at the math behind the scene. If we represent the stem as the function f and the input as x, then without the skip connection, the output is fx. Well, with the skip connection, the output becomes fx plus x. Let the desired true label to be y, we are essentially learning the residual, which is fx equals to y minus x, which is like the first-order Taylor explanations. And this is where the residual names come from. It works as a refinement step and learns how to adjust the input features for the high-quality features. Ultimately, it allows us to build deeper neural networks. So the residual block in the ResNet follows the VGG's full 3x3 convolutional layer design. And the residual block has two 3x3 convolution layers with the same number of output channels. And each convolution layer is followed by a batch normalization layers and a ReLU activation function. Then we skip these two convolutional operations and add the input directly before the final ReLU activation function. So there are two types of ResNet block. One type is the regular ResNet block, which is the ResNet block with identity function. And the other type is the ResNet block with one-by-one convolution. We usually mix them together during our architecture design. Within the ResNet blocks, we can also try different permutations. We can insert a batch norm layer before, in between, or after the convolutional layers and the ReLU activation function. And nowadays, it's very common to say these three layers tightly combined together as convolutional layer, batch norm layer, and a ReLU activation. So the original paper describes several possible number of convolution layers in one ResNet. And the smallest one is the ResNet 18. Here, 18 means there are in total 18 convolution layers in the network. And the input step has 2 convolution layers, and each stage has 2 basic blocks. Each basic block has 2 convolution layers, so that add up them together to be 18 layers. Besides, we can generalize ResNet to any size of layers. Broadly speaking, a complete ResNet consists of 3 components. So first is the input stem, which consists of 1 convolution and a max pooling layer. A second is the 4 stages of repeating ResNet blocks. At the beginning of each stage, we reduce the size of the feature maps and double the number of channels. And remember that we can reduce the output feature map size by tweaking the strat parameters in the convolutional layer. If we want to keep the output feature map at the same size as the input, we can set the strat to be 1. And to reduce the output feature map to have half of its height and width of the input, we can set the strat to be 2. And to be more specific, for the first to the 4th stage, each convolution layer of each stage has 256, 512, 1024, and 2048 channels, respectively. After the final stage of the ResNet blocks, we get an output with 512 channels. And now we pass the data through a global average pooling layers, which reduce the feature maps on each channel to be 1 by 1. And finally, we connected the resulted 512 numbers to 1,000 outputs for the 1,000 class with a fully connected layers in the end. And in this 3 component, the first and the third components are fixed, while we can easily play with the number of blocks in each stage in the second components. So we can stack up the same basic blocks for multiple times and form the main parts of the ResNet. As we can see, the variation like ResNet 34, ResNet 50, ResNet 101, or ResNet 152. The deeper the model is, the higher the accuracy it can achieve, but the larger and the more burdensome the model will be. And that's all for the ResNet. If you are interested in more details, check the ResNet sections in the detail box. So here are the parameter size comparison between the convolutional neural networks we have been talking about so far. As you can see, ResNet is the smallest model with 60,000 parameters, and AlexNet's parameter size increases dramatically to 60 millions, since we have much more neurons in each of its fully connected layers. And VGG double the size of AlexNet, it keeps the same number of dense layers and the same number of the neuron in each layer as AlexNet, but it increased the number of convolution layers to 16 or 19. That's why it gets bigger. However, ResNet make a breakthrough with its skip connection. As we can see, the ResNet 50, ResNet 101, or even ResNet 152 all decrease the number of model sites will increase its number of convolutional layers. What is more, even though ResNet has less parameters, which means it will be faster during the inference, its accuracy is dramatically increased compared with VGGs. Here is a comparison, where the orange dots are the ResNet 18, 34, 50, 11, and the 152. While the blue dots are different layer size of VGG. The higher the dots of the plot, the more accurate the model it is. And the farther the dot to the right, the quicker the inference speed it is. Obviously, ResNet beats VGG in both speed and accuracy. Now, let's get some hands-on practice. Let's see how to use the pre-trained ResNet from Gluon CV Model Zoo and transfer learning the model on our image classification task. Let's open the notebook MLA CV Day 3 ResNet.